All right. Good morning, everyone. I hope you all had a great break. So we'll get started. So first, just want to remind you guys that homework 10 is due tomorrow and by midnight. Okay. So make sure you find some time today and tomorrow to finish the problems there. And the next two homework assignments are also online. So again, these assignments are having just one day less for you guys to work on. So keep notes on the due days for the last three assignments here. And then the final exam is scheduled to be on the 22nd from 10 to 11:50 a.m. So that's also different from the class time schedule. So also make note on that. All right. So today we'll finish chapter 15. We only have a very little section here that we didn't finish last time. And then we'll also look at chapter 16. So on electromagnetic waves. So that's a kind of summary chapter for what we have learned over the past roughly like 1.5 months or so on electricity and magnetism. Okay. So let's take a look on what we learned last time. So last time we introduced the concept of phasor, which is used to describe the voltage and current of an AC circuit. So each element will have its own current phasor and also voltage phasor. Due to the nature that the two might not be, or the two might sometimes not be in phase with each other. All right, so basically you'll have a vector that represent the maximum of that quantity. So for example, V max that represent the maximum of the voltage. And then this vector, maximum vector, will rotate counterclockwise with the angular speed of omega, which is the angular frequency of the AC circuit. All right, and then the voltage at any given moment will be the y projection of this maximum vector. We call it phasor here. Okay, so that's a sine function. Similarly for current phasor, which is the vector has the maximum, the magnitude of the maximum current, I max, and then that's rotating with the angular speed of omega. Okay, so I max phasor and V max phasor, depending on what element you have. For a resistor, you have them in phase, so they're having the same directional angle all the time. While on the other hand, if you have a inductor or a capacitor, then the voltage phasor and current phasor, they are not in phase. So that means there's an angle between the two. Okay, so in this case, if you are a capacitor, then the current is leading the voltage by 90 degrees. So then they have current phasor here, then you have voltage phasor over here. Okay. And so if you have if you have a RC circuit, then you can draw the phasors for the resistor and then the capacitors on the same diagram over here. So because for RC circuit, the resistor and capacitor are in series, so their current phasors are the same. So the I max is the same there. For the voltage phasor on the resistor is I max times R. That's in the same phase as the current. However, for the voltage phasor for the capacitor, it's lagging by 90-degree angle. So it's this guy. Okay, so that's the voltage phasor for the capacitor. Then the overall phasor, voltage phasor for the circuit should be this guy, should be the I max R, this yellow vector plus this red vector. Then it's the brown here. So you have two vector add up, you want to do the vector addition over here. So because these two are having an angle of 90 degrees, then you are doing kind of the Pythagorean theorem for the diagonal of the total V max. Okay. All right, which turns out to be the total V max is equal to the total I max times this square root of R squared plus XC squared So this is the impedance of the RC circuit. All right. And XC is the capacitive reactance that we learned earlier. Okay, so impedance Z equal to that. And if you look at for the power consumed by the whole circuit, you'll find that it's going to be just I squared rho mean squared times R, because the capacitor does not consume any power. And if you write that in terms of I in terms of V RMS divided by Z, then it's I RMS V RMS times R over Z, which we call R over Z to be cosine phi here. That's the power factor of this circuit, okay? All right, on the other hand, if you have RL circuit, you'll be having this similar scenario here. So in this case, the voltage on the inductor is leading the current by 90 degrees. So then the voltage phasor is this blue on the inductor, and then the voltage phasor on the resistor will be the yellow phasor over here. So the overall again will be this diagonal line here, the one in brown. So it turns out the Z is going, in this case, the impedance for RL circuit is going to be R squared plus XL squared, okay? Similar to the RC circuit. And then the V max for the RL circuit, the total circuit will be equal to I max times Z. And we also took a look on if you have R, a resistor, an inductor, and a capacitor, they are all together in series in an AC circuit. Then in that case, because the inductor that has a voltage that leads by 90 degree, however, the capacitor has the voltage lags the current by 90 degree. Okay, so the current vector is this green. The voltage on the resistor is the brown again, and then this red, or you say pink, looks like more like pink here, is the voltage phasor on the capacitor, and then the blue is the voltage phasor on the inductor. Okay, so it turns out the impedance for the RLC circuit is going to be R squared plus XL minus XC square, and then square root of it. Okay, all right, so I think that's what we learned last time. And then again, you can similarly calculate what's the power factor here. So it's again R over Z. Okay, so all these scenarios, if you have RC circuit, RL circuit, or an RLC circuit, it's going to be R divided by the total impedance Z. All right, so that's power factor called cosine phi. I think we have mentioned that. Now, if you have a RLC circuit, you know that the current, RMS current is equal to VRMS divided by square root of R squared plus XL minus XC. In the case if XL equal to XC, then you have maximum current, RMS current, okay? So when that happens, that frequency is called the resonant frequency, because RL and XL and XC are functions of frequency. Okay, so you can tune the frequency so the two equal to each other, and that frequency you have resonance. And for your the radius in your car, either it's a FM or AM brand, so it's basically using that frequency, resonant frequency, to capture the maximum signal. Okay, all right. And this is a plot of the RMS current as a function of the frequency. Okay, when you are at frequency, resonant frequency, you have maximum current. Okay, this curve is for the if your R is smaller, and this is if you have a relatively larger R. Okay, then this flatten out quickly. All right, so the next section in this chapter talks about transformers. So basically, when the electricity is generated at power plant, okay, it's at relative high voltage. So in this case, this is a figure, probably the European country figure. This is 12 kilovolts, okay, but at the consumer end, at the household over here, it's using 240 volts. Over here in the States, we are using 120 volts, okay, but similar here. So you can see the power plant as 12 kilovolts. The household is consuming 240 volts. Okay, so you are having different voltage. So this is being achieved by using transformers in between. Usually, when the power is delivered through larger distance, higher voltage is utilized to minimize the dissipation of the energy. Okay, so first from the power plant is the voltage is being stepped up to higher voltage. So then you use a step up transformer. Okay, and then after that it's going to be stepped down to a lower voltage that is delivered to the household. Okay, so there's a step down motor here. This is still 13 kilovolts, and then there's a further step down transformer here to the household. Okay, so several transformer will be used. Now, so a step up transformer basically increases voltage, while the step down transformer will decrease the voltage. Okay, so this is schematic drawing of a transformer. Inside it, you have coils on the primary circuit, and then you have coils also on the secondary circuit. Okay, so if you want to increase the voltage, then you will have less number of turns over here. You have more number of turns over here. So this is again, this is using Lenz's law. We will take a look on that. So here, the cross-sectional area here, and then on the primary circuit here, and then the secondary circuit here are the same. So then the if you have current going through here, then there will be magnetic field generated. Okay, so through this metal material over here, so you are confining your magnetic field in this parts over here. So that's the same magnetic field over here and here. All right, if you have less turns over here, then flux over here is less, the total flux, because total flux will be number of turns of coils times the flux through each coil. Okay, and then they add up. So what you get for the voltage on the secondary coil will be, according to Lenz's law, will be minus. Okay, the total flux change in flux times ns over delta t. Voltage on the primary is also governed by Lenz's law. So it's equal to the minus number of turns coils here, delta phi over delta t. Delta phi over delta t is the same term. So you can set up that in that case, this equation, Vs over Vp is proportional to the turns of coils, okay, Ns over Np. So this is a transformer equation, all right? Basically, you can use the number of turns on the primary and the secondary to determine what will be the ratio of the voltage on the two sides, okay? If you see this symbol in a circuit over here, this is then the transformer symbol in a circuit, okay? All right. The power in both circuits, in the primary and secondary circuits, they are the same. So that when you set it that up, so P equal to V times I. So VP primary times IP primary should be equal to V secondary times I secondary. Okay. So then the relationship between the voltage, the currents on the secondary over current on the primary should be equal to inversely proportional of their voltages ratios. Okay, Vp over Vs, because V times I are constant. Okay, and you can see then if you have number of turns of coils, then currents on the secondary over current on the primary should be equal to the number of turns coil on primary divided by the number of turns of coil on the secondary. Okay, so this is a more complete transformer equation for relating both current and voltage with the number of turns of coils on the two circuits. Okay, all right. We will take a look on one simple example here. So this one says the electric motor in a toy train requires a voltage of 4.5 volts. Find the ratio of turns on the primary coil to turns on the secondary coil in a transformer that will step the 120 volts household voltage down to 4.5 voltage. Okay, so you want to bring 120 volts to 4.5 volts. So it's looking for a number of turns of coils here. All right, so you're going to use the transformer equation. All right, you're looking for NP over NS. All right, that should be directly proportional to the voltages VP over VS. Okay, it tells you you want to bring down the 120. So 120 is your household voltage divided by 4.5 voltage that delivered to the toy. Okay, so that simply will give you 26.7. Okay. All right, I think that's a relative simple one, but still, if you have questions, let me know, okay? All right, so if you guys are clear with that, we'll then take a look on chapter 16 here on electromagnetic waves, okay? All right, so let's take a look on chapter 16. All right, so this is again the summary of electricity and magnetism. So it was in the 19th century that James Maxwell, he developed a theory that explains all the relationship between electricity and magnetism. And he also predict that visible light is caused by electromagnetic waves. So basically light is magnetic electromagnetic waves, or we call EM waves, okay? So so then somebody was making this joke that when God made light, he basically says those four equations, the Maxwell's equations, okay, because those equations describe the property of electromagnetic waves, okay. All right, and it was first observed by Hertz when he experimentally determined that the you can actually generate and receive EMF waves. Okay, so to generate a EMF wave, you use a AC power supply. Over here, you have RLC circuit. Okay, and then this is the what you have for the coils here as part of the transformer over here. Right, this is a secondary. So on the secondary, there's this gap over here, spark gap over here. So if you have AC signal here, you produce AC signal over here, which gives you the changing magnetic field, okay? And then the changing current over here gives you changing magnetic field. And you can have a tuner over here, which is also an RLC circuit somewhere here inside. You can tune to the same frequency and then capture that signal, okay? All right. So for the electromagnetic wave, it's described by those four equations are called Maxwell equations. So the first one is the Gauss law for electrostatic. Okay, so if you have charge in space, then there's electric field produced by the charge. So that's governed by Gauss's law. And similarly for the magnetism, so if you integrate through a closed surface, you'll get, in this case, you'll get zero because for magnetic field lines, they are closed lines, okay? So if you have a closed surface, you'll figure that it's going to be zero. Now, for the changing of magnetic field, we know that you can have changing, if you have changing magnetic field, then you can induce electric field. Okay, so this is called Faraday's law. All right, and then also for Ampere's law, if you have currents, then you'll have magnetic field. So that's Ampere's law. Okay, so this is basically a summary of what we learned for the previous chapters. Okay, so we will take a look again, kind of review one equation after another. So for the electric field lines, so this is what you get. If you have charge, then you have electric field that is coming out of positive charge and then ends at negative charge. Okay. However, for magnetic field lines, they are closed lines. So you can imagine if you have a closed surface and any surface over here inside magnetic field line, you'll see that for same amount of lines go into the surface, they will exit out of the surface as well. Okay, so the total, if you do integration of B field through a closed surface, then it will give you 0. Okay. On the other hand, for Gauss's law, you on the electric field lines, you'll get charge. Okay, if the surface encloses any charge, you'll have that. Okay. All right, and Faraday's law. So that gives you the EMF for a change in magnetic field or change in magnetic flux. Okay, so then you'll have um, the electricity generated or EMF generated. Okay, now EMF can be also calculated by integrating through a closed path of the electric field. So then in this case, you'll get electric field inside the loop as well, okay, in the wire, in the conductor in that case. So for the first equation, Gauss's law, it's equal to the Q enclosed divided by epsilon naught. So that means charge. If you have charge, then it's not equal to 0. So sometimes this is also referred to monopole for the charge. However, for magnetic field, there's no magnetic monopole there because it will go to 0. Okay, because for the nature of the magnetic field lines, they are closed lines. So then when you integrate through a enclosed path surface, it'll give you 0. So the conclusion is there's no magnetic monopole, but there's electric monopole. Okay. The other two equations, Faraday's law and Ampere's law. Okay, so if you have a change in magnetic field, then you have electric field induced. Okay, now is the reverse true? If you have a changing electric field, would you have changing magnetic field? The answer is yes. Okay, so if you have changing electric field, you'll get changing magnetic field. Okay. So this is what we have. So if we have a capacitor, okay, so here in this case, now if there's current going through here, that means there's electric current, then you will induce magnetic field, okay, because of the current. As the charge builds up over here across the capacitor, so there's electric field generated, okay. Now you can see if you have changing electric field over here, that means as the process of the charging process, then you actually have changing magnetic field because the current then will be changing, right? The current when the charges are building on this charge, so there will be changing of current over there, okay? So if you take a closed loop that enclose just one plate, not the other plate, all right, then you'll see there's a problem here because physically you don't have charge go from one plate to another plate. Okay, so in that case, actually the current is going to be 0. However, you still have the B field over here. So that means you should still have a current, right? I, okay. So if you have events like this, okay, we then call this to be the current because that it's not a physical current, right? But we call this as a displacement current. Okay, if you have changing charges on the two plates, that leads to a current going into here. Okay, so then it will actually have a changing electric field over here, which would induce a magnetic field because the changing electric field will give you current changing over there. Okay. So in that case, we kind of introduce the concept of displacement current over here. So then that gives you this guy. So if you integrate through closed path over here, then it's equal to mu naught epsilon naught d phi e over dt, which is equal to mu naught times id. Again, I displacement. All right. So with that, then we should rewrite the Maxwell, Ampere's law of the Maxwell's equation. We need to do a revision of that. So integration of B field, the magnetic field through a closed path is equal to mu naught times the physical current plus this part is the mu naught times the induced the displacement current due to if you have changing electric field. Okay. So this is electric flux d of dt. So that means changing the electric flux. Okay. All right. So again, so this is the what the displacement current is equal to. ID is equal to mu naught epsilon naught d phi over dt. Okay. Actually, I think that's not mu naught over here because this should be mu naught times ID. Okay, ID should be just epsilon naught d phi e over dt. Okay, that shouldn't be mu naught over here. All right, just make note of that. Okay, so it's this guy. All right, so then after we modify Ampere's law, then this is a complete Maxwell's equation describe the electricity and the magnetism. Okay. What happens in the vacuum? So in the vacuum, there's nothing in the vacuum. So that means there's no charge, no masses. Okay, so in that case, then the first equation simply because the vacuum Q will be zero. So then it will be equal to zero. Okay. And the second equation remains the same. The third will remain the same. But the last one here, because it's in vacuum, there's no physical current. Okay. So then there's zero over there. However, the second term will remain. If you have electric field changing, then you still have that. Okay. So now you have changing electric field or electric flux, then you'll have magnetic field. So if magnetic field can be changing, then you'll generate again electric field. Okay, so that's how electromagnetic wave can propagate in vacuum. If there's still nothing, but if the two fields are changing, then you can still have the waves propagating in vacuum. All right. So quickly, last semester in chapter 16, we talked about the wave functions. Okay, so if you have wave, we use y for the wave function as a function of space and then also a function of time t. Okay, space x and then time t, and the speed is involved. Speed of that wave is involved over there. Okay, so you can have a sine function or cosine function as a solution for this wave function. Okay. So then applying this wave function to an electromagnetic wave or EMF wave, so then you can get the solutions to the wave function. So for electric field as a function of space and time, so that should be equal to a peak value times a sine function, or in some textbook, you may be seeing a cosine function. Okay, sine of kx minus omega t. All right. And then for the magnetic field, it's also a sine of space and time. So with a peak value in magnitude, sine of kx minus omega t. So if electric field is in the y direction, then the B field will be in the Z direction. That means E field and B field, they should be perpendicular to each other. Okay. According to these two equations above there, that's what you get. Okay, this is the result. Okay, we are not going to go through the deviations, but if you solve the two simultaneously, you will get this the solutions to the electric field and then also the magnetic field. Okay. All right. So in that case, again, I think this is a repetition of what we had in the earlier slide. So if you have to satisfy the wave function, so then the solution would be the max a sine function or a cosine function. Okay. All right. So in the case that E is in the Y, then B should be oscillating in the Z direction. Okay, so this is the X direction. This is the propagation direction of the wave. Then the E field should be in the Y direction. B field should be in the Z direction. Okay. So the two have a very simple relationship for the magnitude. E should be equal to C times B, where C is the speed of light, because light is simply EMF wave. Okay, so that's equal to roughly 3 times 10 to the 8th meters per second. Okay, so at all times this should satisfy. Okay, because you say solve the two equations simultaneously, or or they both satisfy this equation. Okay, the wave functions. All right, where the k is equal to 2 pi divided by lambda, and then c is equal to its omega divided by k. Okay, so omega is 2 pi divided by t. Okay, k is 2 pi over lambda. All right, so this is whole spectrum for EMF wave. So it's basically from radio waves to the infrared waves, and then visible lights are the very small band over here, and then the ultraviolet, the X-rays and gamma rays. Okay. All right. So the visible light, if we zoom into the band, this is what we get. Okay. So something from roughly 700-ish in nanometers for the wavelength, and then down to 380 something in nanometers. Okay. All right. Now again, let's take a look on the production of EMF waves. So if you have electric dipoles, if you have two pieces of the metals, if you connect them to the AC current, so then you will have like positive charges at given moment on this one, and then on the other one you have positive charges. Okay, so an AC circuit, power supply will have the positive and negative alternating all the time with sign functions. Okay, so then you'll have a E field in between these two that is varying as a sign function. Okay, and as a result, because you have varying electric field, then you will generate magnetic field. Okay, so the blue here are the magnetic field. If you have two charges that is varying or changing, like one moment it's positive on the top, and then another moment sometime later it's negative on the top. Okay, so you have that varying electric field will generate varying magnetic field, and the generate varying magnetic field then will generate varying electric field again. Okay, so for that reason, then you have EMF generated, okay, by varying the poles. Now for the receiving end, so if you have antenna, receiving antenna, so this is connected to a loop. So then when the EMF wave hits over here, for example, the electric field hits over here, so then you will have changing the electric flux, all right, inside the loop there. So then that will generate changing current, will receive the signal, okay, to the receiving end. Okay, so basically, on the other hand, if you have magnetic field being going through here, then it's varying over here in the loop, then you'll generate varying electric current. In that case, then will be received. Okay. For the energy of the EMF waves, so we learned that earlier that if you have energy in electric field, then the energy density is proportional to field square. Similarly, for magnetic field, energy in magnetic field is proportional to the density, the magnetic field square. So then the two will add up to be this. Okay, so 1/2 of epsilon naught E field square plus 1 over 2 mu naught B field square. Okay. Now, when you have maximum for electric field, then you'll have minimum for the B field. Okay. So you can also express for the average, you are going to be using the root mean square quantities for the fields. Okay, just similar to for when you have an AC circuit, we are going to use the root mean square quantity for the current and voltage. All right. And also there's this relationship E equal to C times B. So then you can express the average just solely on the RMS quantity of electric field or RMS quantity of the B field. Okay, so in that case. All right. Now, if you have the electromagnetic wave hit on a surface or a light hit on surface, then there's energy delivered to the surface. Okay, you can calculate what's the intensity by doing the total energy divided by the time, impact time, and then divide by the area. Okay, and that would be equal to U AC over delta T. Okay, so this is the energy density times the volume. So this is the volume, the cross-sectional area times the length of this cylinder divided by the area divided by T. So that gives you energy density times the speed of light. Okay. All right, so you have energy delivered to the surface, then you can also express this in terms of momentum. So momentum then will be equal to the energy divided by the speed of light. Okay, so U total U over C. All right, so in that case, you can see there's pressure called radiation pressure on the surface equal to force divided by area, where force is delta P over A times dt. Okay, so then this is delta U over CA dt. Okay, because delta P is equal to delta U over C. Okay, so then that equals to I over C, intensity divided by the speed of light. All right, so and I think I just briefly and quickly go into chapter 16. So let's take on a video there. Maybe it may help you guys understanding it better. Okay, so I'm going to play this video for you guys.
By the 19th century, we were pretty sure there was something going on between electricity and magnetism. First, in the early 1800s, Michael Faraday showed us how a changing magnetic field induces an electromotive force, or EMF, resulting in an electric current. He also found that electric fields sometimes act like magnetic fields and developed equations to calculate the forces exerted by both. In the mid-1800s, Scottish physicist James Maxwell thought something interesting was going on there too. So he decided to assemble a set of equations that held true for all electromagnetic interactions. And he did a great job of it, compiling a set of equations as critical to physics as Newton's laws of motion. And while he was coming up with his all-encompassing equations, Maxwell predicted the existence of electromagnetic waves. And these are the waves that help you view the world around you, talk to your friends 1,000 miles away, and heat up that midnight breakfast burrito you've been craving. So Maxwell and his equations are, to put it simply, enlightening. When James Maxwell created his dream team of electromagnetic equations, he started with the ideas and the mathematics that other physicists had already established. But he put them together to create a new, complete understanding of electromagnetism. Maxwell's first equation is a form of Gauss's law, which states that the electric flux through a closed surface is proportional to the total charge enclosed by that surface. A closed surface, in this case, is just the surface of any shape that completely encloses a charge, like a sphere or any other three-dimensional shape. And electric flux is a measure of the electric field that passes through a given area. Mathematically, this equation says that electric flux is the integral of the electric field over the area of the surface, which is equal to the enclosed charge divided by the permittivity of free space. I won't blame you if you don't remember, but the permittivity of free space is a constant of proportionality that we've used before, that relates electric charge to the physical effect of electric fields. If the electric field is a constant over the surface, then the left side of the equation becomes E times A. Maxwell's second second equation is also a form of Gauss's law, only with magnetic flux instead of electric flux. Magnetic sources are always dipoles with a north and south pole, and magnetic field lines that leave from the north pole and return back to the south. When you're looking at how a magnetic field interacts with the surrounding surface, you see that the field lines that leave the surface out of the north pole must enter back through the surface to reach the south pole. This results in the overall magnetic flux being zero. If you compare this with Maxwell's first equation, you can tell that the format, with the integral of the magnetic field over the surface area, is the same, but here the integral will always equal zero for a closed surface. Now, Maxwell's third equation doesn't have anything to do with Gauss's law. Instead, it's Faraday's law, but slightly different than how we've seen it before. This is how we've seen it before. If you remember, Faraday's law of induction says that a changing magnetic field will induce an electromotive force in a loop of wire. Maxwell's version is more general, simplifying Faraday's law to show the value of that induced EMF. It says that the EMF is equal to the line integral of the electric field over a closed loop. So with this equation, you can see the connection between a changing magnetic flux and an induced electric field. The fourth and final equation is one that Maxwell made the most tweaks to in order to make it applicable to all electromagnetic phenomena. Maxwell's first and second equations were so similar, one for electric fields and one for magnetic fields, that he knew there must be an equation that complemented Faraday's law as well. After all, if a changing magnetic flux produces an electric field, why is there not a complementary law saying the reverse? Why couldn't a changing electric flux result in an induced magnetic field? Here, Maxwell started with Ampere's law, which states that the current through a wire induces a magnetic field around a path surrounding the wire. In order to make this equation work for all possible electromagnetic scenarios, Maxwell needed to consider a situation where a magnetic field is induced, but not from the flow of current. For example, picture a charged capacitor that's connected to wires on both sides. As the capacitor discharges, current runs through both wires, generating a changing magnetic flux, just like Ampere's law says. But a changing magnetic flux is also induced between the two plates when there's no wire connecting the plates. However, there is a changing electric field, and it acts like a wireless current. In order to account for the magnetic flux generated by this wireless current, Maxwell added what's known as the displacement current into Ampere's law to complete the equation. Despite being called the displacement current, it isn't really an electric current. It's just called that because it fits into the equation just like an actual current does. Mathematically, the displacement current is equal to the change in the capacitor's charge over time. And that is equal to the change in electric flux over time multiplied by the permittivity of free space constant. With the addition he made to Ampere's law, Maxwell's equations were complete. And using his laws today, we can see a pattern in the production of electric and magnetic fields. If a changing electric field is generated, then a magnetic field is induced, which results in a changing magnetic field that induces an electric field, and the cycle continues. These oscillations are electromagnetic waves, and they're made up of changing electric and magnetic fields that travel through space. Maxwell believed that we could reproduce electromagnetic waves in the laboratory, and he was right. To prove it, let's look at an object that can produce electromagnetic waves and transmit them through the air. An antenna. This antenna is made up of two conductive rods, each attached to opposite ends of an AC generator. When the antenna is operating, the two rods switch between being positively charged and negatively charged as the generator changes voltage. And when one rod is positively charged, the other is negatively charged, and vice versa. When electric current travels up into the top of the rod, you can use the right-hand rule, pointing your right thumb in the direction of the current, to see how the magnetic field flows around the antenna. The electric fields generated by the antenna itself are easier to track, since they'll just go from the positive rod to the negative rod. But as the direction of current switches, the direction of both the electric and magnetic fields change. And as the rods switch their charges, the waves generated by the initial charge distribution continue to propagate away from the antenna. So if you were standing away from the antenna, you would be able to measure an electric field and magnetic field that are both constantly changing. Now, what would that look like? To grasp the effect of changing fields in motion, let's model an electromagnetic wave as it travels through three-dimensional space. First, note the direction that the wave is traveling in the x direction. Now plot the electric field oscillating back and forth in the y direction. The electric and magnetic fields always act perpendicular to one another, so the magnetic field will oscillate in the z direction. Note that the electric and magnetic fields both peak at the same time, so they're in phase. These electromagnetic waves are a type of transverse wave, which means both fields, electric and magnetic, act in directions that are perpendicular to the direction in which the wave is moving. And how fast do these waves travel? Maxwell calculated that the speed of each wave is equal to the electric field's magnitude divided by the magnetic field's magnitude. This equation simplifies down to an equation with two constants, the permittivity of free space for electric fields, epsilon naught, and the permittivity of free space for magnetic fields, mu naught. And this speed works out to be 3.00 times 10 to the 8th meters per second. We write it simply as small c, and it's the speed of every electromagnetic wave ever. At least in a vacuum. You may know it better as the speed of light. After all, light is an electromagnetic wave. Every electromagnetic wave carries energy through space and can reflect off some material while passing through others. But visible light is just one small part of what's known as the electromagnetic spectrum. Like waves in the ocean, electromagnetic waves can vary in their wavelength, amplitude, and source. The wavelength is the distance between the peaks of the wave, and the frequency is how many times a wave peaks in a given second. You might remember when we talked about traveling waves that a wave's speed is equal to its frequency times its wavelength. And since the speed of light is constant, you can easily find the frequency if you know the wavelength and vice versa. Now, in order to calculate the energy carried by any electromagnetic wave, you need to know the magnitude of the electric and magnetic fields that compose that wave. Specifically, you use these magnitudes to calculate what's known as the energy density of each field, which is the amount of energy stored in a field per unit volume. Then you can combine the energy density for both fields, solving for the total energy per unit volume within the wave overall. But since you know that the strengths of the electric and magnetic fields are directly related, you can substitute the electric field magnitude for the magnetic field magnitude, and vice versa. This lets you come up with the energy density terms that encapsulate the energy in both fields with fewer variables. So here's the calculation of the speed of light that Maxwell found, and the constants that it's simplified down to. You can take our energy density equation and substitute the magnetic field magnitude B with the electric field times the square root of the permittivity constants. With this simplified energy density equation, you can then substitute the electric field magnitude for the speed of light and the magnetic field magnitude. These equations give the energy density of an EM wave at any point during its propagation. One last important measurement of delivering energy is intensity, which is the energy transported by a wave per unit time per unit area. Mathematically, the energy delivered, delta U, is equal to the energy density times the volume of space in which the energy is transported over a period of time. You can then replace energy density with one of the simplified equations we used earlier. So the volume of space encompassed by the wave is equal to the unit area times the distance travelled. And the distance travelled will be the speed of light multiplied by the time period. After cancelling out like terms, you're left with an equation that tells you how much energy you have per unit area based on the strength of the electric field, which you can also replace with the magnetic field magnitude. A lot of math, I know, but the vast knowledge of electromagnetism that we have today and the doors it has opened into the fields of relativity and quantum theory are all based on the theories that Maxwell and his predecessors developed. Albert Einstein praised Maxwell specifically for his contributions, but it was the combined effort of revolutionary minds like Maxwell, Faraday, and Gauss that we have to thank for our understanding of the interaction between electric and magnetic fields. Today we learned about Maxwell's equations and their unifying power in the field of electromagnetism. We discussed electromagnetic waves and how changing electric and magnetic fields propagate through space. We investigated the different types of waves on the electromagnetic spectrum, as well as how to calculate the amount of energy they can carry. Crash Course Physics is produced in association with PBS Digital.
All right, I think let's summarize chapter 16 here. So, any questions you guys have? All right, so if not, we'll just stop here for today, and then from tomorrow we'll be talking about optics. Okay, so see you guys.